Hello everyone. In these chapters, we are going to study the giant planet formations. We have studied the growth of a protoplanet by considering the accretion of planetesimals onto the protoplanet. The gas of a disk only works to slow down the velocity of a planetesimal. Once a protoplanet increases the mass, the gravity becomes strong enough to capture gas of a disk as an atmosphere. We will study the formation of atmosphere in the first section. In the second section, we study the structure of atmospheres. The mass of the atmosphere increases with the mass of a protoplanet, which will be called a core of a planet. When the gravity of gas exceeds the pressure, gas flows into the atmosphere, forming a gas giant planet. We consider the critical core mass to start gas accretion onto the protoplanet. The last topic is the gravitational interaction with disk. First topic is the formation of atmospheres. In the Hayashi model, the velocity of gas molecule in a protoplanetary disk is expressed by the sound velocity as a c equal to the 9.9 times 10 to 2 meter per second at a distance from a star is a 1 AU. A gas molecule is trapped by the gravity of a protoplanet when it is within the boundary radius given by these equations. If the 1 over c squares minus gravitational potential energy of the Gm over r is larger than 0, the gas can escape from the gravitational field of a protoplanet with a mass of the capital M. So critical radius of a protoplanet is given by the boundary radius of the r sub b's. And the r sub b is given by this equation. So 1 over c squares is equal to the Gm over r sub b, boundary radius. So left hand side is a kinetic energy and right hand side is a gravitational potential energy. These two energy is equal. So gas can kept by a protoplanet. So r sub b can be calculated. Gm over c squares. So it becomes 400,000 kilometers when the mass of a protoplanet is Earth size at a equal 1 AU. Then we'd like to find out the condition for atmospheres. Radius of a protoplanet is calculated from these equations. Mass of a protoplanet can be calculated. The volume 4 over 3 pi times r cubed. This is the volume of a spheres times the densities of materials of a protoplanet. Using these equations, you can find out the radius of a protoplanet with these equations. The radius of the protoplanet can be calculated about 8,000 kilometers when the mass of the protoplanet is the Earth mass. This radius is a little bit larger than the Earth's radius due to the low densities. We use the density of the materials is a 3 gram per cubic centimeters. A protoplanet has atmosphere when the following conditions r sub b is the boundary radius is larger than radius of cores. So in these situations, we consider this is the radius of the cores. The boundary radius is here. Then the shaded region corresponds to the atmosphere. This is the condition for a protoplanet to have an atmosphere. We can find out the mass of a protoplanet normalized by the Earth mass is larger than the 2.3 times 10 to minus 3. Then the protoplanet start having an atmosphere at 1 AU from a central stars. So we derive the conditions for a protoplanet to keep an atmosphere. If you change this equation with the radius, radius should be larger than about 1,000 kilometers. Then protoplanet start having atmosphere at 1 AU. The minimum size of the protoplanet is decreasing function with the distance from stars. Because the sound velocity is also a decreasing function of a distance from a central stars, speed of the gas molecule is becomes slower in the outer regions from the central stars, and a protoplanet can easily keep the gas molecules as an atmospheres. Minimum size of a protoplanet that have an atmosphere is decreasing with a distance from a central stars. So I draw the log R. This is the critical size of a protoplanet, which has a atmospheres is decreasing function with the distance from a central stars. Then you might find the gap at the snow lines, gap due to the change of the compositions. In the regions, density of the materials, we use a 3 gram per cubic centimeters, because the main composition of the material is a rock. In the outer region, density is we use 1 gram per cubic centimeters, because ice is our main compositions. So we could find the gap at the snow lines. A smaller protoplanet can keep atmosphere due to low temperatures beyond the snow lines, and also the low density of materials beyond the snow lines. It might be important to take into account the effect of atmospheres of a protoplanet when we consider the growth of the protoplanet, especially in the outer regions. Okay, this is the end of the first sessions. We studied the formation of atmospheres.